line, and then they start hearing about you. Oh, your company's looking for so-and-so? I met this this person from UBC Okanagan, phenomenal student. Let me tell you more about them. And now you've got an in, now you've got something that's going to separate you from the masses and from the stack of applications. What industry has said, by and large, they don't like is going through 300 to 400 to 600 applications to try to find the suitable candidate. If you can set yourself apart and you've got someone that can vouch for your character, vouch for your professionalism and your integrity and your commitment to the program, you've already set yourself apart, and they don't want to spend the time unless they have a huge HR department, then they have people dedicated to it. But a lot of small to medium-sized business, and especially startups, they don't want the time to go through that stack. They don't have the time. They want to know who's going to be a good hire, who's going to fit in around the water cooler, and who's going to gel with their team environment. And that's stuff that you can't put on paper. That's a feeling you get from knowing someone and sending an email and being like, hey, I know you're interviewing. I met Sarah last week. Let me tell you, this kid's a firecracker. She knows her stuff. She's on point. She'd be a huge asset. If you don't hire her, we will in a year. That's the kind of conversations that happen. Okay, any other questions? Yeah. Yeah, so you'll get access through emails that I generate. So we do 2 formal events per year. And last year we included you for the first time ever in the big Vancouver Student Union Career Fair, which had like over 200 and something people represented, like vendors. So you'll get those emails from me, and they'll also be updated on our website under professional development as well. Okay, so and those are good events. That's a great chance to get there. And it's also really cool to have your mentor wear them too, because sometimes they can attend or you can talk about what you heard. Hey, you know, so-and-so from Fortis said this is a big hiring trend going on. What is your opinion of it? What do you think? And now you're coming across as an informed student who's not just like, how do I get a job? Which is, again, not what you want to say. Okay. Good questions, though. All right, I don't want to take too much time because I know you guys have a busy lecture. I'm going to throw up the QR code. Trust me, investing in yourself now for the long-term, long game or long-term payoff is really, really advantageous. It's a smart choice, and we're very aware. We support the program. We have some asynchronous resources in the background. We have topics and themes to go through. And we're moving away from a transactional relationship where you're like, can you look at my resume, look at my cover letter, to you get to know me as a person, because that is going to last you for 20 years. Looking at your resume, proofreading a cover letter, they'll do that once and then they'll smoke bomb, you'll forget about it, and they'll ghost you. Right? You want to commit to a relationship so you stay in contact with this person as your career develops and as theirs does. Last thing, we have over 300 mentors, everything from local startups to the big names of Google, Facebook, and who else do we have on there? I think Tesla had someone sign up. So some big companies, multinationals, either way. So it's got everything in between. Okay, it's really worth checking out. Yeah, thank you. Time's up. Professor's been very gracious. So there's the spiel. If you have questions, grant.toper@ubc.ca, email me. Honestly, you owe it to yourselves to put some effort in so you come out of here with some contacts and a network, along with your technical brilliance, which of course is a given. Thank you so much.
Okay, thank you very much. So let me ask a question of the people online first. A second. Yeah, all done? Yeah, all done.
Thank you, everyone.
Okay, so can you still hear me for the people watching the lectures online? Okay, good. All right, let's continue on the lecture here. I just want to finish one more example on the time invariance, and then we'll get on the new topic, which is called convolution. So when you do the checking for time varying or invariant, we want to check, right, if y of t minus t naught equal to mx t minus t naught. So this is what we want to check to make sure this is time varying or time invariant. And of course, you need to, on a bit of a same picture, x is the input, y is the output, right? Okay. So let me show you one more example. This one here, we have used it for linearity. So now let's use the same example to check this time varying and time invariant. Here's a system, and this system must look familiar to you because we checked linearity for this system. We used the superposition to check, and it turned out to be a linear system. So now the question is it a time variant or is it a time invariant system? Okay, so as we have stated, we need to find out what this term equal to and what this term equal to, and then compare each other. We can make a decision. The y of t minus t naught is always the easy one, right? This one is always a little bit a difficult one. So let's first check, what does this give us? So this one, I think, again, to jog your mind, right? So essentially, this is a delayed input, right? This is delayed input. So that's what's asking, what will be the output corresponding to this delayed input? Okay. So let's do this. And there was a student asked a question here, because in my lecture, I sometimes, instead of directly deal with the actual input, I introduce a new function. In this case, let's call it xd of t. Right? So we introduce a new time function. So this time function inside a bracket, there's no t minus t naught, it's just a t. So this will, to somehow reduce a little bit of complexity, right, at the beginning of the computation. But I'm not changing the question though. So let this equal to this, then basically your original question, which is what we want to find out, becomes, right, try to find m of xd of t. So xd of t is the input. So you go back to your original system. Here's your original system. Your original system output is related to input in this fashion. So of course, your input now changed from x to xd. That's only change. So this is essentially mx of t. Right? So this is mx of t. Your input is changed from x to xd of t. And you look at the actual output here, you find all the x, and you change all the x to xd. Okay. So that's purely based on the system. Now we had to deal with what is xd of t minus 2, what is xd of 2 minus t. So you can, for now, you could write it separately, just then before you can put them together, back together, right? So what is xd of t minus 2? Okay. So this time, you go back to your xd of t. So you can see here, your xd of t equal to x of t minus t naught. So it's always, you look, observe, what is the difference? The difference is, here's a t, here's t minus 2, right? So your t is being changed to t minus 2. It's not a specific number. I mean, you could just say t changed to 3 or 4, right? But in this case, the t is changed to t minus 2. So what do? You go back to the right side. You look for all the t, not x, the t. You look for all the t and change the t to t minus 2. Okay, that's basically replacement, right? X t to change this t to t minus 2. So this t here, right? is changed to t minus 2. And then the 2, sorry, sorry, that's what I'm doing here. What is it? Minus no x, yes, that's right. And then minus t naught. Okay. Yeah. Yes. Y is what? This one here? Why is this 2 not t naught? Okay, so you got to observe where this 2 from, right? This is this term I'm dealing with here. And this term comes from where? From your original system. You see here? This is your original system. Original system y equal to m of xt equal to this expression. Now I'm dealing with m of xd of t. Can you see the difference? Right? So if this x changed to xd, so what should I change to the output? X to xd, xd. Right? So this is how you get xd of t minus 2, xd of t minus 2 minus t when your input is xd. So the only symbol change basically. Right? This is where this is from. And then you deal with what xd of t minus 2 is, which is what we're doing right now, right? Is that good? Is it clear? Raise your hand if it's not clear. That's okay. I'll take it as clear. I'm sure it sometimes it takes a little bit of time here to adjust to the substitution, right? So what to substitute, okay? So your principle should be, right? What am I dealing with here, right? So you see here, m, inside m, this is basically the input to the system. And then when you're dealing with this term here, xd, this is the, you can call it the input to the xd function, or you can call it, this is just a variable change or value change to the function. It's very similar to this. I mean, this is a function too, but of course, that's input to the system. This is some sort of value change to the function. How do you make the change? Then you observe, right? So right now the change is from x to xd, and this one just changes from t to t minus 2. So t to t minus 2. Right. Okay. So similarly, if you deal with this term here, the xd 2 minus t, so you go back to your expression for xd of t. You're going to try to look for the right side, look for the variable t, and you replace the t with which term? 2 minus t. So now you come 2 minus t, and then you keep the t naught as it is, minus t naught. So now you can put these two terms together, and you get your m x of t minus t naught, and equal to x of t minus 2 minus t naught plus x 2 minus t naught. Okay, so this is basically one side of the time varying or time invariant property checking. Look at one side, and then let's look for the other side. And the other side is y of t minus t naught. Okay, this is the other side. The other side is always the easy one, as I always say, because you are, right, you have, as I said, you have original y of t. This is your original y of t here. What's the change? What changed from here to here? That's right. The t is changed from t to t minus t naught. So we did this review. This literally means you're shifting the whole signal to the right by T naught amount. So if T is changed, you go back to the left, the right side. What do you look for? You look for all the T and you replace all the T with the change, which is T minus T naught. So that I get X, find this T minus T naught. And find that T. So that's the change. Okay, once you've done this step, and don't take it for granted, they're all the same. So because this is 2 minus bracket, you see the difference here, right? The difference, the first term, you look, compare those two expressions here. The first term is the same, huh? Yeah. But the second term here, this is 2 minus bracket T minus T naught. And here is 2 minus T naught. So apparently they're different, right? The second term. So then you can immediately conclude that this is not the same as this. That means the system is time variant. So for now, the challenge, right? The way I can see challenges is that because you're starting learning this brand new, is to get your brain used to substitutions, okay? And you look at what needs to be substituted, right? Because I think every one of you should be very comfortable when you're having function, you know, x equal to t squared. If I just ask you to, I think everybody knows what to do, right? But the challenge is sometimes is if I ask you to do this instead of a number, and that's what I find sometimes students get confused, right? So you should stick to the principle, right? Just see what has been changed. Then you do the replacement corresponding to the change. That's the point. Okay. So that's time varying and time invariant. Now, I want to combine two things together now. Okay. So if you recall, we learned about system linearity. So system linearity, there's essentially basically two properties needs to be satisfied: additive and homogeneous. If these two properties satisfy, it's a linear system. So now we have learned the property of time varying and time invariant, right? So if I combine these two properties together, so if you combine the system linearity and the system TI together, time invariant. If it's basically, if you have a linear system and you have also a time invariant system, when you have both properties satisfied, then you end up with a system called LTI. It's called a linear time invariant system. And this is a very common, I wouldn't say this is a very common system you typically will start with when you're learning signals and system and controls, right? However, in reality, in real life, most systems are not linear time invariant system. Okay? It's a very ideal system, but it's a very representative system. So in this class, right, this is where we're starting. So this class, we mostly will deal with LTI system. Okay? So in reality, most systems are nonlinear and most systems are time variant, unfortunate. But to understand LTI from the beginning at the starting point is very actually important to understand better of more complicated systems. All right, so Now I'm going to give you a slightly different example, okay? This example will be an example how you apply the system properties to obtain certain output. So consider that we have a LTI system, so whatever the system should be. So let's just say the system has an input and output, but we know the system is LTI. Right? So now I say, okay, here's the input. Let's call this is X of t. And the input is a box signal, rectangular box. Number 2, yeah. And we already tested, given this input, I obtain an output. Okay. So that's the output here. It's a triangular output. My joint is a symmetric. Okay, let's call symmetric. Did I hear humming or somewhere? Oh, my ear is too sensitive. Okay. So here's your input, here's the output, right? So now I have a new input. So this new input, let's call this is original input. Let's call this new input, let's call it x1 of t. And this new input looks like this. Rectangular box. See, use a red color maybe. So 1, 2, then okay, here's the new input. Of course, the question would be, can you plot the new output? So essentially, you plot it, okay, based on all the graph that are here. That's a slightly different kind of question because previous questions are mostly to ask you to prove, to show if the system is linear, system is causal, if the system is time varying or time invariant. Right? But now this time, you're told that the system is LTI, and then you are asked to find the corresponding outputs based on the known original input, original output, and the new input. Okay, so this is a typical example of how you can make use of an LTI property to solve this question. So how do I solve this question? To solve this type of question, the number one step, okay, the most important step is to find out the relationship between the new input and the original input. Okay. So if you remember, you know, system linearity additive means you have x1, x2, right, equal to m x1 plus m x2. Right. Right. So you see, if a system linear, you have this property. When you add two signals together, you can get the corresponding output by doing the right side. So that's what I mean by trying to get, can we get the relationship between this x1 and x of t first? Then we can make use of some of this LTI property, right? So this skill at here, definitely you need a little bit training sometimes, or need a little bit observation, better observation. Some signals are easy to observe, but some maybe needs a little bit more a training experience in order to get it, right? There's not a very, systematic way. But let's observe this here, right? So let's observe x1 of t. Between 0 and 2 for this portion, right, for this portion here, can you tell me this portion, how is this portion related to the original input? It's the same, right? Excellent. So I've already got one portion of the input. Now let's look at the next portion, this portion here. Okay. How is this portion, so just focus on this part, how this portion relates to the original inputs? Let's hear from, I forgot your name. Josh, right? Yes, go ahead. To the right. Yes, right? So this part here is you can do it both ways. You can flip it, right? Flip it and then shift it. Or you shift it and then you flip it. Okay. So flip means you add a negative sign in front of the whole function. So essentially it becomes negative x of t. That's flip, right? You had to use the right wording. I think if you look at my tutorial number 1, there's a flip. There's also a wording called a reflection, right? Reflection means you have to reflect around which axis. Okay. So now, if you can observe this, then things are definitely getting easier. So you can see my x1 of t is an addition, essentially two boxes, right? The first box plus the second box, and outside this area is all 0. And then the first box is basically your original x of t. The second box, okay, as we have just observed, what do you need to do? You need to flip this first, or a shift. But let's do the flip. You flip it around about the t-axis, and then you shift it to where? To the right by how many units? By 2 units, so t minus 2. So that's the second part. Okay, now if you are at this stage, if you're not very clear, I could also basically, if this is x of t, then do a few more steps, right, to make yourself more comfortable. So negative x of t you get. Okay, you get this. And then one more step. Negative x t minus 2. So that means this is a shifting of this one here by 2 units. That's how you step by step, you would be able to get the graph, huh? Yeah. Okay, let's get back to this. All right, so once I get this, then where should I go then? So I can see now my input signal, new input signal, is an addition of 2 signals, right? 2 signals. You can call this as x, you can call this as number 1, you can call this number 2. That's pretty much what we have here, right? You have 2 signals, 1 signal plus another signal. Then according to the additive property of a linear system, although this is a plus, but that's okay. I mean, you can pull a plus to minus, but then, right, that doesn't really affect the things. Just for observe, this is minus here. So then according to the additive property, the results, right, the results would be mx1 plus mx2. Now, of course, you could also think about the superposition, right? So here's number 1, the coefficient here is 1, the coefficient here, if the coefficient here is -1, it's okay, right? You know, C1, x1 plus C2, x2, the superposition property, okay? Yeah. So in other words, according to the, according to linearity, when your input is x of t, let's put this minus here, x of t minus 2, right? When your input is this, then it should be the same as m of this minus m of x of t minus 2. That's purely from the system linearity. Good. So now I'm ready to do some plotting now. So basically ask ourselves, do we have m of x of t? Yes, we do, right? We already have it here from the original system. Okay. So I'm gonna just plot it over here. So this is your original input output. So this is your m x of t. Okay. Second part, what about this part here, right? This part. Do we have m x of t minus 2? Because we don't have it right now, okay? But you look at this one here, what's the input? The input is x of t minus 2. So this is a shifted input. So which property should I use now? So basically m x of t minus 2, what would that give us? According to what property we have just learned? Time invariant property. Because we said this is a linear time invariant system. So now I say according to time invariant property, TI property, this signal should be the same as y of t minus 2. And then y of t minus 2, that's easy. That's shifted version of this original, right, to the right by 2 units. And of course, I have a negative sign here. So then you flip it around the t-axis. So now you get is that 1 or 2? 2. So this red one here is negative y of t minus 2. So that's how you can cascading this information by making use of the LTI system property, right? And then you get your corresponding output. So this kind of as I mentioned, this kind of a question, the first step is very important, right? So you have to be able to observe and derive the necessary relationship between the new input and the original output. And we'll have a little bit more exercise later, especially when we learn convolution and we do it graphic approach. We do a lot of graphical manipulations between the functions, right? Okay, so I want you to exercise a little bit yourself. I will just change the questions very slightly. Suppose I'm creating a new input. Didn't change too much, right? So the box for x2 of t here is -3. I want you to plot y3 of t, y2, the corresponding output. Right? All right. I'll give you that as an exercise that this shouldn't take you too much time if you can observe what the output here related, how it's related to the original inputs. Good. Any questions on the system properties? So that's pretty much all we want to cover in terms of system properties. 3 different types of system, 3 properties. How do we check, verify each one of them? Right? What are the tricky parts, right? So the definition, I always recommend start from the definition and then get to the details of how you can manipulate mathematically. So let's now look at the new topic now, okay, convolution. So the first part of the course, as I mentioned in the first lecture, okay, deal with some really very basic concept of signals and systems. So whenever you talk about the signals or systems, a very important part of the operation is processing. So you have a raw signal and you process it and you get a new signal. Right? So this processing skill or tool or technique, there's so many. So there's just so many different ways you can manipulate the signal. The simplest way is you can just flip it, right? You can shift it, right? You could multiply the original signal by a number, right? We call it amplification, right? So those are very simple operations with the original signal. And convolution, okay, is nothing different from a typical processing. It's just a little bit more mathematical, abstractly mathematical involved, okay? So this is essentially a way of processing signals. So now you might wonder, so why do I use a convolution? What's so good about a convolution processing? Now this is a loaded question, right? I can certainly find you some examples that show you, okay, so look, here's the original signal. If you do a convolution, here's what the resulting signal will look like. Okay, now that might actually, it's like, let's say you have an image, you process it and you get a better image, right? Yeah. So convolution is basically a technique like that. You can process it, you end up with something you want. Not necessarily it becomes sharper, it becomes clear, but it's just a signal. You're trying to extract some features out of your signal. Okay. So for now, I always say is try not to dwell too much on what's the benefit of these things here, right? And I can guarantee you will see some benefits, especially you go to electrical or you do some future processing. Okay. And this is also particularly useful for LTI system. Okay, so now let me show you the definition first, and then we'll look at how we can apply this convolution to signals. Okay, so definition is for two given causal signals. So let's say we have two signals which are causal. So signals are represented by functions, right? Basically, you're given two functions which are causal functions, okay, representing two causal signals. And let's call it f of t and g of t. And now convolution is denoted by f of t with a star in between and then g of t. So f convolute g, and the math behind this symbol is you do this integral. There. Okay. And that's how convolution operation is defined. So let us thinking first, and the first impression of this expression of this math formula, okay, is definitely not as appealing as a nice, a cake or something. Nobody likes to see this, to be honest, right? but then we'll get used to this, okay, what this exactly is. Okay, before we dive in, let's look at this integral, okay? Essentially it's the integral, right? Now, before I talk about integral, maybe get back to the causal signal first. I mean, what is the causal signal? Causal signal means this function should be 0 when t is less than 0. Same thing, the other function should be 0 when t is less than 0. And that actually is part of the reason why this integral here starts from 0, right? Because everything beyond t minus 0 is all 0, right? So it doesn't really matter. And this integral, let's get back to the details here. For this integral, okay, can anybody tell me what is the dummy variable here? And this symbol, what we call this symbol, tau, right? This is dummy variable, right? Can I use a different symbol? Yes, you can, right? You can use a K or W or S, whatever you want to say, use. But a convention typically we use a tau at here. Okay. And then the function here, the limit is 0 to t, okay? 0 to t here. So if you can try to sort of like visualize in your head, suppose you have a function f of t, you have a g of t, right? And you plug it into this integral and you carry out the actual integral. So what do you think the results from this integral should be? Should it be a constant number, or should be a function of a tau, or should be a function of what? Of t, right? So that's excellent. That's what you should really be clear. The resulted value of this convolution is still a function of t. Okay, so maybe let me write down a few more words here. So it results in a function of t. So you can call this anything you want, and for example, you can call this as w of t, right? Yeah. So now we're clear on the same page. So convolution is an operation between two functions, on two functions. And the results, forget about the actual operation yet, and the results is another time function. Right? And this new time function obviously will be different from your original, okay? So that's called processing. So essentially, for example, you have original f of t, and you also have another g of t. You want to do something to your f of t, and you tried the convolution, then you resulted in w of t. And this w of t supposed to give you a little more information, okay, other than what you have directly seen within f of t. That's basically what it is. So now the question now backs the question is, how do we calculate this integral? Okay, how do we calculate the integral? I mean, technically, if I have a function, let's say if this is t, this is t squared, then I will be able to plug it into this integral and then try the integrations as if you have learned in 173, right? Yeah. So that's certainly traditional way to do this, no problem at all, okay? But in this class, okay, we're gonna try a graphical approach, okay? So we'll try graphical approach. The part of the reason is a lot of time the functions that are given are not just a simple like a t squared. A lot of time the function given is a piecewise function. So like the boxes, like this kind of function here. Like this. This is something we call this piecewise, right? Between 0 and 2, you go 1. Between 2 and 4, you go -1. Okay. So for this type of function, piecewise function, graphic approach is much more easier to use than a traditional integration. Okay. So I don't have time to start this graphic approach, but just to bear in mind what we're going to do, we're going to use graphic approach. I'll show you with an example how to conduct this graphic approach to calculate convolution. Okay. Any questions? Okay. Thank you.
So, as you said, that this one is time variant. This question we did.
Yes.
Like 2 minutes.
Yes.
But it's still trying to figure out,
Hmm.
is it just because this signal, this sign has changed? Is that the reason why we're saying it's time?
I mean, strictly speaking, right? The property is not satisfied.
Yes.
Then our conclusion is time variance.
Okay.
Right.
But like, if we look at specifically for this case,
Yeah.
it's like basically the sign is getting changed, right?
Yes, and part of the reason, right? You know, it's hard to visualize this, but as you can see clearly, part of the reason when you have an input is x, xd is this.
Yes.
And then the delayed input results in the output of this. And over here, and that's what the replacement of t calls this, right?
Yes.
And this part, that's actually what I mentioned. You got to be careful when you do the change. This t here, you get this, but then when you do the t change based on the regional outputs, and you get different replacements. You see here, right?
Yes. Yes.
Because when I do the replacement t based on regional outputs, I find the t, I get this, right? But then over here, when I do the t change, t minus 2, okay, and that I'm looking for the sorry, where am I? Sorry, the second term. The second term, yeah. When I look for the t change to 2 minus t, yeah. Like the second x d of t equals to this. Oh yeah, right, sorry. Yeah. So this is your x d of t, right? Yes. So when you x d of t is 2 minus t. 2 minus t. So you replace this t with 2 minus t. Right? Okay. So that's why for now, your hand has to be very clear. What is your xd? What am I replacing, right? And then you're dealing with this term. What's y? And what am I replacing? Right? It's all about correctly identifying the substitute, the new substitution based on this current, expression. Yeah.
Yes.
Yeah. Good. Yeah. All right.
So, is this the correct hardcode?
Yeah, that's right. I mean, the drawing may be yes, because you can see if you really draw this correctly, it's probably not going to be too hard, right? Because the slope will be different, right? So there might be a little bit,
Yeah.
change of slope.
So it will become this way. It's not the cam of x of t minus 3 because it's coming like 3 down and then it's shifting to the right.
Yes.
So that's the final equation. The drawing would be something like this.
Yes. No doubt.
Thank you.
Good.